Hi guys, welcome back to Physics 210. Okay, today we're going to look at the last part of our last chapter, the part 2 of the law of thermodynamics. Okay, so this one is chapter number 7. The last part will be this one here. Okay, 7.3 second law of thermodynamics, the Carnot cycle, efficiency of engine, heat pump, and so on. All right. Okay, the first one is our second law of thermodynamics. Okay, second law of thermodynamics. We look at not a general statement yet. Our general statement will be the second part of thermodynamic law, second law of thermodynamics. Okay, this one is based on RJE Clausius statement. Okay, Clausius statement about second law of thermodynamics. We look at what this law stated. Okay, we write it like this here. So the second law of thermodynamics, okay, states that heat will flow spontaneously, from high to low temperature, okay, and the reverse, is not true. Okay, the reverse is not true. All right. So that means it cannot do the reverse. Okay, it cannot do the reverse. All right. Even though you heard of what reversible engine, right? But that is not true. That is our second law of thermodynamics. Okay. So at the moment we are just using this Clausius statement under this second law of thermodynamics. Later on, after we finish everything about the heat engine, refrigeration, everything, then we go into more detail about what actually is second law of thermodynamics in a general statement about something called the entropy. Okay. All right. So that is our first part. Now after that, that is our first one. Our second part is the heat engine. Okay, the heat engines. So what is heat engine? Well, the idea of heat engine is to do work actually. Okay, is to do work. Well, you can see that, for example, before you go into heat engine, you can do something very simple like if you rub your hand, if you use this one to rub on a piece of rubber, and then what you are doing is, by doing some work like that, rubbing your hand, rubbing this one against the paper, okay, you are actually producing heat. You are doing work to produce heat. So work to heat is a very easy process. Okay, work to heat. Okay, from work producing heat, easy. Okay, it's easy. Okay, it's very easy. But to do the reverse, heat to produce work done. Okay, this one is difficult. Okay, this one is difficult. The one that is easy because it's only involve one thing, friction. Okay, it produces friction. But the other one, from heat to work, okay, is difficult because you need something as a medium. So this medium is normally called mechanical system. Okay, mechanical system. So that's why we call it heat engine. Okay, heat engine. All right. So now we start with the idea of heat engine. Okay, what is the idea of heat engine? Okay, the idea of heat engine is we need to have a high temperature reservoir. Okay, high temperature reservoir something that contains the high temperature energy. Okay, so let's assume it is at temperature T high. Now, as we know from closest statement that if the heat flow, okay, it only flow from high temperature to a low temperature. Okay, to a low temperature. So this one we call it the low temperature reservoir. Okay, low temperature reservoir, TL. Alright, and in the middle, okay, we need some mechanical system so that it can do work. This is our machine, we might call it a machine. Okay, might just as well call it a machine to be simple, or just some engine. Okay, some engine. Okay, some engine. So this one is to do work. Okay, to do work. So what we need here is this. Okay, you must have heat flowing from the high reservoir to the low end of the reservoir, low temperature. So from high to low. Okay, but what happened is this one here is a lot of energy compared to the one that transferred to the lower temperature reservoir. The purpose is part of the energy will be used to move the engine, to move the mechanical system. So if I use a wider arrow, it will show what happened here actually. Okay, and what this is what happened now. And this one become smaller. So you see the size of the arrow. So here we have this heat input from the high temperature. We call this one the Q high, and this is a heat output. This is a wasted energy. So this one is a Q low. And the difference between them, there is a difference because work is done here. Okay, work is done here. Alright, so something like this. Okay, something like this. Alright, so we have this high temperature reservoir. Okay, and then this one is the heat energy coming from the high temperature flowing towards a low temperature end of the system, which is the QL later, because part of it is used to do work. Okay, is used to do work. And if you look carefully, all these symbols here are given a modular sign because they are all positive. Okay, so in our system here, our second law of thermodynamics, the heat engine, we use only positive value. Okay, so do you remember this? Our QH, our QL, the work done, they are all larger than 0. Okay, they're all larger than 0. All right. Okay, so that is the idea of this heat engine. Okay, so now we need to look at the next thing is the usefulness of heat engine. Now, heat engine, okay, number one, okay, only useful. Heat engines are useful, okay, are only useful if it runs, okay, or if they run. Okay, if they run in a repeating cycle. Okay, if they run in a repeating cycle, if they only one run cycle, what's the point? Every time you run your engine in a motorbike, you have to come down and push and start and push and start. Might as well just walk your leg. Okay, so that's number one. Only useful if they are in a repeating cycle. That's important. Okay, number two is something that you must know ideally about this engine is that in each cycle, the change in internal energy delta U is equal to 0. Okay, why? Simple, because okay, it returns to the original or the starting state. Okay, because you return to the same state. So in a same state, then your change in kinetic, the internal energy will be 0. Okay, so these are the two important things about our heat engine. Okay, but of course these are based on ideal condition. Okay, these are based on ideal condition. Okay, now now after you know the heat engine type, now when you hear the word engine, of course it must be related to real life engine. Example engine are like car internal combustion engine. We have a gasoline or petrol engine, and then we have diesel engine. Okay, and before this type of internal combustion engine was invented, there are other type engine. The most famous one is a steam engine. Okay, so we're going to look at two type of engine. One is a steam engine, another one is our what we call that, the internal combustion engine, and we only look at the petrol engine. Okay, now the next one is type. Okay, number 3, types of engine. Okay, type of engine. The first type, okay, A, this is the steam engine. Okay, steam engine is we have two types. Okay, steam engine we have two types. The first type is reciprocating type. What is reciprocating? The one that you look in the movie, the type that you are running the train and so on, you have a piston moving in and out, right? Okay, for example, something like this, reciprocating engine. You have a tank contains water, right? You heat up the water. Okay, you heat up the water, so this one started to change into steam, and this steam is used, okay, to run a piston. Okay, to run a piston. So this piston will be pushing out and then pull in again, and then it started to what we call that, to move a heavy wheel. Okay, it started to move a heavy wheel so that the train can move, or any mechanical system will move. Okay, so and then you have to have exhaust. Okay, exhaust, and then this exhaust will not to call exhaust. This one is the output. This output here, when the piston is moving back, it need to have a steam coming out. Okay, they need to have a steam coming out from the system and then condense into water again. Okay, condense into water again. So this condensed into water system is called a condenser system, and then this one will be pumped back into here. Okay, it will be pumped back into our boiler. We call this one boiler. Okay, and then recycle so that there's no wastage. Okay, it should look something like this. Okay, something like this, you can see that. Okay, so what happened here is the boiler, you boil the water and then it turns into steam. This is a high temperature end, and then it go into intake valve. Okay, intake valve, this is where the intake valve is here. It must be synchronized in between these two. Okay, and that valve open, it pushes the piston out. At the same time, this one is closed. Okay, so when they reach the end of the cycle, it started to return back, right? If you return back, this one had to close and this one open. So when this one open, it pushed the steam out. Okay, and then collected in the condenser. This condenser here are normally colder section. So what happened here is the steam will be condensating. That's why it's called condensation process. Happen here to return to water and then pump back. So what you realize is this one is at a lower temperature compared to this one here. This one is not only high temperature, it's also at high pressure. Okay, so imagine if you started to boil a system and you don't allow to gas to the steam to come up, the boiler will actually explode. Okay, it happens all the time actually. Until now, still happen like that. It's because of the mechanical failure or ignorance of the person who actually handle the engine. Okay, so this is our reciprocating type. Now another type, the second type is the turbine type. Okay, the turbine type is actually mostly used nowadays in a system to produce electricity because they are much simpler. We still have this boiler, we still have this condenser, the pump. The only thing changed is this part here. Okay, so the one that come here, okay, is going to pass through a turbine system. A turbine system is actually something that looks like this. Okay, something that looks like this. The turbine can spin. Now what happens is it will actually cause the turbine to spin when the gas or the steam at high pressure and temperature pass through here and then exit through the other side, and then it go to the condenser and then back to the boiler again. Something like this. Okay, something like this. Of course, it's not only one turbine. In a complete system, you have more than 100, maybe 1,000 of all these blades all put very near together. The purpose is to increase the efficiency of the turbine system. Okay, so that is our the type of the engine, the steam engine type. Okay, so steam engine, why turbine type is more preferable? Because it got less moving part. It's not that, it's only spin, nothing else. This one you have a lot of this mechanical system connection and so on, and then everything must be synchronized. Okay, and this one is more direct. It's more direct. The only thing that we are facing here is the high pressure section of the turbine. Okay, so that one, if problems started to occur when it is still spinning at such a high speed and with such a high moment of inertia, this thing can actually kill. Okay, things fly out. Okay, you can imagine a very heavy stuff rotating at high speed and then suddenly come out loose because of bearing fail and so on. So the person work there might fly together with a wheel to heaven or maybe to hell. Okay, we don't know. All right, next one is B, the internal combustion engine. Okay, internal combustion engine. Okay, for our internal combustion engine, okay, it's quite the same as the reciprocating type. Okay, reciprocating type, we have something that looks like this. You need to have a cylinder. Okay, a cylinder. Okay, let's say we draw a cylinder like that. Okay. Okay, this is the crank. This is a cylinder head. The piston is inside here. Okay, this is a piston with the seal we call the ring, and this is a connecting rod. Okay, the connecting rod is to connect to a flywheel and a crankshaft so that this thing can spin. So you see, put horizontal, it looks exactly the same. The only thing different is this have also the only thing different is it have one spark plug. Okay, and then you have two valves here, the one that you can open and close. Okay, you can open this hole and close. Okay, according to the timing needed. Okay, according to the timing needed. Okay, let's assume this is an input. Okay, and this is the output. So this output is the exhaust. Okay, this is the exhaust valve, and then this is the induction valve or the input valve. Okay, induction valve. So we call this one the intake. Okay, so this one intake, air will and fuel will go in, and this one will be exhaust. So this valve here related to the intake and exhaust is called the intake valve. This is called the exhaust valve. They will have spring and they have some rocker and something to push them in and out. Okay, at very high speed, depending on the engine speed. Okay, you have one more thing here, which is the spark plug, which is connect to high voltage. The spark plug has a purpose of produce spark to ignite the air fuel mixture inside the or above this cylinder head. Okay, or above this cylinder head. All right. Okay, so this is some the reciprocating engine. Okay, sorry, internal combustion engine. This one is a petrol type. Now, if you look at a more complete diagram, it looks like this. Okay, it's going to look like this here. Okay, so there are. This is called a 4-cycle. Okay, 4-cycle internal combustion engine. This is a petrol type. Now, first, you need to start the engine, right? You turn the key, the starter to move, or you kickstart a motorbike. When you kickstart, initially your piston will be at any position here, but mostly will be at this relaxed position, either the this one or this one. Okay. Now, when you kickstart, it started with this system here. Okay, it start with any actually, but we start from this one. So this is when the piston is moving downwards. Okay, what happen is the intake valve is open. Okay, open, and then the gas air mixture. This gas means gasoline. Okay, gasoline, mixture from carburetor, okay, and then it moves down until the rod is actually vertical at lower end, okay, at the lower end, and by this time the both valve will be closed. Okay, both valve will be closed. This one is closed just now, this one open, but now both closed, so that when the wheels move again upwards, the piston is compressing the gas air mixture. Okay, it compresses the gas air mixture to getting a higher and higher compression, okay, pressure. And then by the time this one reach a very high at the top, we call the top dead bottom, top dead, okay, the top dead position, this spark will ignite, will fire a spark, it produces a spark, cause the mixture of gasoline and also the air to burn and explode. That explosion is going to push, okay, push this piston downwards, okay, push the piston downward, and then at the after that by the time it reach this position, the lower position again, it's going to move up, and then this exhaust valve will open. When that open, the exhaust gas will be pushed out, and then by the time it try to come down, it return to this one again. Okay, this one close, this one open, so that now it take in a fresh gas air mixture and the cycle repeat itself again. So how many, why we call 4 cycle? Why we call 4 cycle? When you can see five figures here, actually the first cycle is this one. This is one of the cycle. Okay, this is one of the cycle. Intake, see or not? It take in gas, or you can start from here actually. Okay, take in gas. These are take in, right? And then this is called the compression. Compression. So first one is intake, induction stage or intake. Intake here. Compression now. Ignition, expansion, and exhaust. Okay. So the engine here. This is an old type of engine. Okay, this is an old type engine. A lot of old cars still using this type of technology, using spark plug, using this one intake, carburetor. Sorry, okay, carburetor. But a modern one, they get rid of the carburetor. They are now changing to the what we call that fuel injector. Fuel injector. So fuel injector, it still have the intake valve, exhaust valve, spark plug, except it has another nozzle go into the engine to spray the fuel when they are under compression, either before the spark plug ignite or sometime during the spark plug ignite. Okay, normally it's before, so that they can heat up the mixture. Okay, so that one is our internal combustion engine. Yeah, so that is roughly what we have for this one. All right. Okay. Other type of internal combustion engine is quite the same as this one. Okay, for example, diesel. Okay, diesel don't have spark plug. Okay, it get rid of the spark plug. So what you actually have is a diesel injector. Okay, something like a fuel injector. Okay, so diesel injector replace the spark plug. So why? When you take in the air at room temperature, you compress it to a very high compression, normally 1 to 20 times the volume is compressed, so the air will heat up so high in temperature that when you spray the diesel in, the diesel will be burned instantly. Okay, that's why you don't need, and that's why you don't need this fuel what we call the spark plug. And then the rest are the same actually. Okay, the rest are the same. Okay, and because of that, diesel engine actually is much more efficient than gasoline engine. Okay, so but nowadays efficiency is like they are competing with each other. But why somebody like diesel engine, somebody like petrol engine, is all up to preference. Somebody like electric car, somebody like bicycle, and somebody don't even like themselves. All right. Okay, so now that is our type of engine, the internal combustion engine. Okay, internal combustion engine. Okay, so now we need to look at the efficiency of engine now. Yeah, the efficiency of heat engine. That is number 4. Efficiency of heat engines. Okay, The symbol for efficiency of heat engine is small e. Okay, it is small e. Now it is defined. We define this one here. Efficiency of engine or heat engine E is the ratio of work done by the engine, okay, W, to the heat input to the engine from the high temperature side or high temperature reservoir here. Okay, this one. Okay, so that means E is equal to work done over Q high. Okay, but we also know one thing. Okay, we also know that, but Q high, okay, the one that input from the high temperature reservoir will be used to do work, and also some of it will be wasted at low temperature N. Okay, so that means our Q high, our work done is equal to, so that means the work done is equal to Q high minus Q low. So our E will also become Q high minus Q low over Q high. So E is equal to 1 minus Q low over Q high. So we have two equations for our efficiency. Okay, which one you use depends on which information you are given. So I'll call this one number 1 and this one number 2. Okay, so that is our page 1 for the efficiency of heat engine. Okay, efficiency of heat engine. So we continue on looking at this equation. Look at the heat engine efficiency, E value. Okay, so now we look at this efficiency is 1 minus Q low to Q high. Okay, Q low to Q high. Now E is in between. Okay, E is in between 0 and 1. Okay, 0 and 1. 0 means 0%, 1 means 100%. So if you want to use percentage, what you need to do is just multiply the number with 100%. Okay, but here we're looking at this one. Now if you want to have 0%, it's actually very easy. So if you look at if number 1 here, if your QL is equal to QH, the output, the wasted energy is equal to the input energy, that means you are not doing work. So efficiency is equal to 0. Okay, is equal to 0. Is equal to 0. Now the second thing is, if your QL is equal to 0, your efficiency will be 1. Okay, so this one is 0% and this one is 100%. You see, you want to have 100% efficiency, you must not waste any energy. No energy wastage. Okay, no energy wastage. That will be the requirement to have 100% efficiency or efficiency engine equal to 1. But according to Kelvin Planck's statements, or we might call it as well as third law of thermodynamics, it's impossible to reach absolute 0. You see why? Why absolute 0? Because later when we look at Carnot cycle, you will know that meaning. Okay, you will know that meaning. Okay, so it's impossible. Yeah. So this one, practically, okay, practically for engine, okay, to achieve, okay, for engine to achieve E equal to 1 is impossible. Is impossible. Okay, so if it is impossible, but at least we need to have some hope, right? We need to have some hope. So Carnot cycle is the hope. Okay, Carnot cycle is an ideal engine cycle that is actually idealized by Carnot. Okay, by Carnot, just to give us some light into the study of ideal engine. Okay, so now we look at the ideal engine. Okay, Carnot engine or Carnot cycle. or Carnot cycle. Okay, this Carnot cycle or Carnot engine actually is comprises of what? Okay, a cycle. Okay, a cycle that consists. Okay, a cycle that consists of two isothermal processes and two adiabatic processes. Okay, that is the Carnot cycle. Alright, so if you look at the graph of that cycle, it looks more or less like this. Okay, you look at the PV diagram, right? If you look at the PV diagram, you remember PV diagram, you have isotherm, right? So let's assume you have a isotherm of two temperature different here. Okay, two temperature different, this one. Okay, this one is the T high. Okay, I use two color, yeah. Okay, T high here. And the blue one is a T low, lower, colder, higher, hotter. So it starts from somewhere. Okay, you start from here, a cycle that I'll use orange color. Okay, start from here, I call this one point A, and then it's going to move down. Okay, at one adiabatic, isothermal process to B. Isothermal means what? Isothermal means this one here means delta T equal to 0. Adiabatic mean the Q is equal to 0, right? Remember that last few sub-chapter, the first part. And then after that, from B to C, it go through a adiabatic process. There is a C, okay? And then it go back upwards, okay? Go back upward through another adiabatic compression. This one is isothermal expansion. Isothermal expansion. This one is adiabatic expansion. Okay, in this direction, yeah. Here, and after that, go back compression to D, adiabatic compression, and after that, isothermal compression. Isothermal compression, and this one going back to the A, same state again. You see, so this one now is an adiabatic compression. If you look at the line here, there are volume become smaller, volume smaller. This one volume become larger, volume become larger. So this one is expansion, isothermal expansion. Okay, and this one is adiabatic expansion, and then followed by isothermal compression, adiabatic compression. Okay, so the total amount of heat injected into the system, okay, the heat energy enter is called Q high, and then the one wasted here, okay, the one wasted at low temperature coming up from system is Q low. Now if you look at the area below the graph, okay, the area between in the cycle here, this area actually is representing the work done. Okay, it's representing the work done. So because of that repeating cycle, how much work done you can actually calculate. Okay, ideally it's like that. Okay, ideally it's like that. So we're going to have some diagram looks like this here. Okay, here, that is a more colorful diagram. Later I will scan and let you have it. Okay, so I'm not sure whether it against the copyright or not. This one is by Douglas Giancori. Sorry, doctor. Okay, sorry, Professor Douglas. I have to use this one for the benefit of my students. So please, you understand that. Okay. Now that is a more detailed diagram. Later I scan and put inside the WhatsApp to you. Yeah. Okay. So what is the Carnot cycle? That one. What we call that? Efficiency. Okay. The Carnot cycle is studying the ideal engine. So we look at the coefficient of coefficient. Efficiency, not coefficient. Okay, efficiency. Efficiency of Carnot cycle. Okay, Carnot cycle is talking about ideal engine. So we put E ideal. Okay, E ideal is equal to given by this, okay, TH minus TL. Okay, TH minus TL over this one. Okay, and finally you get E ideal is equal to 1 minus low temperature divided by high temperature. Now that is the Carnot cycle efficiency. Instead of calculating how much energy is flowing in and how much is wasted, we look at the higher end temperature and the lower end temperature. These two temperature here is actually the working temperature, the working temperature limit. Okay, so that one is equation should be number 3 already. There should be number, this is our page 2, right? Okay, now that is our what we call the efficiency of Carnot cycle. So it depends on temperature. It's more practical way, but it gives you the maximum efficiency of your system. So to do that, for example, okay, just for example, you design an engine. Okay, you design an engine, and then it operates at these two initial conditions. Let's say you have this during the expansion of the gas or the production of the energy, the temperature, sorry, at the high end is, let's say maybe 200 degrees Celsius. So we need to change this one to Kelvin, is like 473 Kelvin, for example. And then at room temperature, it exhausts out at lower temperature. Okay, lower temperature, let's say 80. Okay, 80. So 80 degrees Celsius. So 80 degrees Celsius, 80 plus 273, you got this 35. Okay, 353 Kelvin. So your ideal efficiency, the maximum efficiency of the engine you design is this much. Okay, so that one is 353 divided by 473, so you got 0. Okay, 353 divided by 473. Okay, okay, 353 divided by 473, this, and then minus 1. Okay, we minus 1. Okay, we got this 0.25 efficiency, 25% only, 25%. So if you want it to be 100%, your lower end temperature, exhaust temperature must be 0. Okay, so that is our Carnot cycle. Okay, so we go to the next one. Okay, the next one is about refrigerator. Okay, refrigerator, and then we also have air conditioner and also heat pump. Okay, so our next one here is refrigerator. Okay, we call this one the number 6, refrigerator. Most houses now will have refrigerator, right? Okay, so what is refrigerator? Well, refrigerator, the idea of refrigerator is like this. The idea, okay, use block diagram here. Okay, refrigerator, you have a box. Okay, it must come in a box. Okay, and then you have a door here. Okay, you have a door here. Okay, we don't care about the door. So we have a box which you're going to put your stuff inside, the food and so on. And then this must be ideally, okay, or in good quality insulation. Now what you need is, you need to have a engine or something called the compressor. The compressor is going to, what we call that, absorb the heat from the surrounding here. So we have this coolant pipe inside here. Okay, coolant pipe. So we have this coolant pipe. Let's say we put coolant pipe like this. Okay, coolant pipe, absorb heat, coolant pipe. This is the idea, coolant pipe. The more coolant pipe, the better. So all the heat will be absorbed by the coolant pipe. Okay, the coolant pipe, which is consisting of coolant inside. First time they use is the Freon. Okay, and then after that, this compressor is going to actually compresses a gas. So when this is a cooling gas inside, cooling gas, when it compresses a gas, it changes from phase of vapor into liquid. And when that happens, it releases the heat, and this heat will be released, okay, behind or below the refrigerator. So that is where it releases the heat. And what happened here is the amount of heat absorbed will be QL, and the amount of heat released behind the refrigerator is Q high, and the amount of work done by the compressor is W. Okay, is W. All right. So we look at the better diagram of our refrigerator. Okay, here, this is the diagram of our refrigerator. Okay, something like this. All right. Okay, so you have this the cooling. This is a cooling coil inside the refrigerator, normally at the side. Okay, normally at the side, and then you have this compressor. This is a compressor. The compressor is to compress the vapor into low pressure vapor into high pressure vapor, not liquid. Sorry, liquid is cannot compress anymore. Okay, so from low pressure vapor into high pressure vapor, and then you see this is the outside. This is a cooling fin behind. Okay, behind the olden day refrigerator. Okay, so I compressed high pressure vapor. So this one, when it compressed to high pressure vapor, it becomes hot, so that it can take out the heat. The heat is to be exhausted to the atmosphere, and after that, it get cooling down, and then it turn into liquid. Now this is the high pressure in the liquid state now. And then it go into the expansion valve. Okay, expansion valve. So this expansion valve is going to turn the high pressure liquid into the gas again, and then started the process of absorbing heat. Absorbing heat. That is how our refrigerator works. Okay, so it's actually very simple. But why nowadays when you open up a refrigerator, it looks very alien to us? Well, when you come to physics, everything is simple. But when you come to engineering, they want it to be efficient. They want it to look aesthetic, look beautiful, and then you want it to be like safe, safe and efficient and so on. All these things come in. It makes things become looks very complicated. Okay, so this is our what we call it, the energy flow diagram here. So you have motor doing the work. This compressor is moving the work, okay, in actually moving the liquid. So work done, and then is used to absorb the heat from the box inside the freezer, and then actually the heat is exhausted to outside. Okay, so as simple as that. That is our refrigerator system. For air conditioner system is exactly the same, even though it looks very different, right? Okay, because you normally go into two what I call two different units. One is outside, one is indoor unit. But if you look at the olden day air conditioner system, which I still have at home here in my workshop here, I'm using the window unit. It's all in one unit. Okay, all in one unit. It is exactly a freezer. Actually, depends on how cold you want it to be. Okay, so that is our freezer. So another one is number 7, our air conditioning system. Okay, air conditioner. Okay, air conditioner, or we call it AC system. Okay, AC system, air conditioner system, air conditioner system. Now, air conditioner system is the same, okay, except we enlarge the scale, right? So we look at the what we call that, the same type like this. Okay, so you can imagine if you stay inside the freezer box, that what we call that thumb there, the compressor, that one is your air conditioner already. So what we need here is this. In your room, okay, this is your room, right? Okay, your room, if it is insulated, then it's good. If not insulated, not really that good. Now your air conditioner normally is at the higher part here, okay, higher part of your building. So this one, you have a a compressor. Okay, compressor doing the same thing, except your cooling coil, you don't go around the whole room, right? You only go through here. Okay, I draw. There is a compressor inside. This compressor, okay, is doing two. Compressor is one thing. Another one is a blowing fan. So you have, okay, I will draw that compressor only here. Compressor here. This compressor is actually moving the fluid inside here. This is what happened here. Okay, is actually you are moving the liquid like this. Okay, you force it to move. Okay, this is a cooling. Okay, cooling. Right, cooling. And then by the time I come out here, now this part will be hot already. This one will be hot. So I'll use a yellow one. Okay, this is a hot, and then after that it's going to go back in a cycle. You are actually moving. You are moving what we call that, the coolant around, moving the coolant around. And then you have two fans. Okay, one fan is here. One fan is to blow, okay, to blow the hot air. Okay, to blow the hot air from here or from the top, suck the whole air in. Okay, air in, and then it blow the cold air out. So that means you're absorbing the heat already. How much heat is being absorbed? This is the movement of the cold air. Yeah? Okay, movement of the cold air. I use a darker one. Okay, this one. This is the movement of the cold air. This is cold air. Okay, and then how much energy is absorbed through the coil here? That how much absorbed is Q low. And then when that one is under compression from low pressure to high pressure under the compressor, so you're going to make sure that the heat is being blown out, right? So your heat, you have another fan outside here. So this one will blow the heat out, okay, to outside of the building. And this one, how much heat is QH? And what is the motor doing? The motor is doing a work W. Okay, it's doing a work W. So that is what happened there. Alright. So that is our air conditioning system. So if you switch on for quite some time, the room temperature will be reduced, okay, because you already absorb the heat energy from inside and then you throw it outside. Okay, you throw it outside. So that is what happened to our air conditioning system. If you look at that, they're actually the same, right? Okay, they're actually the same. Okay, so the next one is number 8 is our heat pumps. Okay, our heat pumps. So what is heat pump? It's just like water pump. Okay, so heat pump normally is not in our country. We don't use heat pump because what happened here is you want to maintain your house at a high temperature during winter. Okay, this is during winter, so everything is cold. Okay, everything is cold. Let's say like minus 10 degrees Celsius outside, and then inside you want to maintain like maybe like 30. You want to maintain 30 degrees Celsius. So what do? Heat up can also. Okay, you can heat up. It will lose, right? It will lose. But as other than that, you can actually take heat from the cold one to the hot one. Okay, what you do is the reverse of your refrigerator. Is it reverse? Not to say reverse. Is the concept is the same, except now you are outside and the winter is inside here. Okay, so you have a heat pump. Now this heat pump will actually absorb heat. Okay, it will absorb heat even though at a lower temperature like that we can still harness the heat energy QL. Okay, so the compressor will do work W. Okay, and then finally the heat will be injected into the house. Okay, and this heat are normally, because it's under compression, so the heat energy is actually quite high. Okay, so now if you look at this thing here, this one, this air conditioning system and this one is actually quite the same, right? Okay, now what happens if come to summer? You can actually reverse this thing and then take the heat from here and go out. So now in country that have winter, their air conditioner is also the heat pump. The heat pump is also the air conditioner. So it functions as a two-in-one machine. Okay, so that is our heat pumps. Okay, the heat pumps, air conditioner, and refrigerator. Alright, so we look at some of the diagram here. This is the diagram of the heat pump. This is the one. Okay, heat pump. See or not? Okay, you actually extract energy at a very cold environment and then input it into a very warm environment like your house inside there. Okay, so that is our refrigerator, heat pump. No more already. Okay, last one. Okay, our last one. Our last one will be continue on with our entropy. That is number 9, right? Entropy and the second law of thermodynamics. Okay, entropy and the second law of thermodynamics. Now we're going to look at what is the meaning of entropy. Okay, but before that, we want to look at process of gas. Okay? Process of gases. Okay, when we talk about process of gases, okay, for example, expansion, contraction, okay, and then whether they lost heat or they gain heat. Okay, so what happened is they have this different state. Okay, we call this one state 1. Okay, state 1, and then they go to this state 2. Okay, they go to this state 2. Okay, state 1 to state 2, they might have this pressure 1, V1, temperature 1, P2, V2, and T2. We know that we can calculate that using ideal gas law, right? Okay, ideal gas law. But upon research, they realize there's something else. Okay, they have something else called the S. Okay, S, entropy. Okay, S1 and S2, entropy. Okay, what is entropy? Well, entropy, you might say it is something like how disorder are things. Entropy is you might also call that the measure of disorder in a system. Okay, so S, PVT we already know. Okay, in from changes of state 1 to state 2, we have change of pressure, we can have change of volume, we also can have change of temperature, depending on what process are involved. But another thing is there is a change in entropy. So S1 and S2 are entropies. Okay, entropies. So the change of entropies is S2 minus S1. Okay, S2 minus S1. Alright. Now, according to Clausius, okay, according to Clausius, okay, according to Clausius, the change in entropy is given by the Q over temperature. That is our equation number 4. Okay, our equation number 4. All right. Okay, equation number 4. This is how we calculate the energy involved in that changes divided by the temperature during that changes. Okay, give you some example. Very easy example. Okay, 1 kilogram of ice melted to water. Find delta S. Find the change of entropy. Okay, so you know ice melted to water. Okay, I forgot to mention something here. At 0 degrees Celsius. Okay, so 1 kilogram of ice melted to water. You need to know what something about that. What is that something? That you are given the fusion. Okay, the what we call that, the latent heat of fusion of ice, okay, of water ice. This one is 3.33 10 to the power 5 joule per kilogram, right? The latent heat of vaporization is 2.257 10 to the power 6, okay, 10 to the power 6. Okay, so we do this calculation here. So we calculate this. Change in entropy will be this Q over T, and we know that the Q is mLF over T, and the mass is 1 kilogram. This one is 3.33 10 to the power 5, and this one is going to give you joule, right? And then after that, you need to divide the temperature, not divide by 0, yeah? Divide by 0 plus 273 in Kelvin. So we see what is our answer. It's 3.33 power 5 divided by 273. So what we get here, 3.33 10 to the power 5, okay, and then divide by 273, okay, 273, okay, we have 1220 joule per Kelvin. That is our change in entropy. Okay, our change in entropy. All right. Okay, so that is entropy. Now, next thing, another example which is much more complicated a bit. So I call another example. Okay. Let's assume you mix two amount of water. Okay, you mix two amount of water. So now, what happened here is you have two container, two beaker contains two different water. Okay, amount is the same. Let's say amount is the same. One is a cold water. Okay, this one is a cold water, but not that cold. So I use cold water. And then another one is warm water. Okay, another one is warm water. Okay, so our cold water here and a warm water, I'm going to pour it into a container. We assume that it is perfectly insulated or ideally insulated. So find the change. Okay, before that, this is a cold water. This one is information about the hot water. Okay, hot water. So the cold water is, let's say, at 20 degrees Celsius, and this hot water is, let's say, at 24 degrees Celsius. Okay, and then the question is find the change in entropy. Okay, find the change in entropy. Let's say their mass will be 0.5 kg. 0.5 kg. Easier for us to calculate the temperature changes. Okay, now how are we going to solve that problem? First, we must find their final temperature, right? Okay, so to calculate the final temperature is actually very easy. Okay, let's start with calculating the final temperature. So we are using mixture method, right? Okay, mixture method, who lost and who gain. When you mix these two together, cold water gain the heat energy and hot water lost the heat energy, right? So finally they reach a final temperature. And this one involve water or specific capacity C, 4186. But we can cancel that later because both are the same water, different temperature only. So we have mass which are the same, so we just put them as M, C, and the one loss is because 24 go down to final temperature, and this one is MC, and this one will be gain. So you have TF minus 20. Okay, so what we get here is this M can be cancelled MC, so we have this 2TF is equal to 24 minus 20, so your TF is equal to this, plus. Okay, 44 divided by 2, 22 degrees Celsius. This is their temperature after mixing. So when we calculate our entropy changes, okay, the changes in our entropy, we must consider this, the one for the hot water and the one for the cold water. Alright, so the total change in entropy, is equal to the change in entropy of the hot water plus the change in entropy for the cold water. Alright, so what's the formula then? The formula will be, this one is a Q hot, okay, divide by how much energy lost by this one, divide by this, okay, divide by this one, the temperature of the hot, okay, plus this one, the energy gained by the cold water, and then what we call that, this one, the temperature is the cold temperature. But that process happen in a range, so we have a problem selecting what temperature. If the temperature range changes is not that much, we can actually take average. So you see what happen is, cold water temperature changes is from 20 going to 22, so in the middle is 21. And then for the hot water, it reduces from 24 to 22, so the middle is 23. So for this one, the average temperature we are going to use is 21, and this one is 23, which is for this temperature, the average temperature. So how much energy is gained and that one? Well, we know that hot one, okay, it actually lost energy, right? So when it lost, you must have a negative sign. So how much it lost, then we use this formula to calculate. Okay, this formula to calculate, it must be the hot one, negative 0.54186, and then the change in temperature is 24 minus 24 minus 22. Okay, and then divide by this one. Okay, divide by this one. Okay, divide by the average temperature of the hot one, which is 23 degrees Celsius, right? Okay, don't forget the 23 degrees Celsius had to be changed to Kelvin. Okay, this one never mind, this one you change to Kelvin, also you minus the 273 to find out, end up the same. So this one plus another one is the one for this. This one is cold, 0.5, so again, right, gain is positive, times 4186, and this one is 23, okay, or 22, sorry, 22 minus 21. The average temperature we choose is 21. Yeah? Sorry. This one is 20. Okay, 20. So we have divide by the average temperature of 21 plus 273. Okay, so you see what we have for the first one. You have 0.5 times 4186 times 2. Okay, and then divide by this 23 plus 273. Okay, we have negative 14.1 joule per Kelvin plus this one. How much you guess? Is it the same? It won't be the same, right? 0.5 times 4186 times 2 divided by this 21 plus 273 is different, right? Is different. So we have 14.2 joule per Kelvin. So what happened here is you will minus this one, minus 14.1. Okay, sorry. Okay, negative 14.1 plus 14.2, you got 0.1, right? So it's positive 0.1 joule per Kelvin. Okay, so what happened here? According to the law of conservation of energy, well, the hot water lost energy and it is absorbed by the cold water. So that's why the temperature here drop and this one increase. It seems like, well, it go according to what we call that, the heat. If you talk only about the heat, then there's nothing go against that law of conservation of energy, right? According to first law. Now the problem here is the changes in entropy of hot water is minus 14, reduces. This one is increased. Even though they are actually have the same mass and then they are mixed together and reach the same final temperature, it means one thing. It means that the total, the change in entropy in a system is always larger than zero in real process, in a real system, okay, by natural process, that is where we come to something more general. Okay, we come to a more general statement of the second law of thermodynamics. Okay, a more general statement of thermodynamics. All right. So what does that statement say? Okay, that statement states this. Okay, it states that generally, generally the change, okay, in entropy, okay, the change in entropy of a system, okay, the change in entropy of a system and its environment must be larger than 0. Okay, must be larger than 0 or equal to 0. Okay, must be equal or larger than 0. That is a more general statement. Okay, must be larger than 0. So we have this change in entropy of a total in a system must be larger than 0. So that means what happened is going to spell end of the universe. So as we know just now, I did mention something on entropy just now. Entropy is the measure of disorderness. Okay, if we look at this, okay, what is entropy? Entropy is more or less like is the measurement, is a measure of disorder. Okay, disorder. Okay, disorder of a system. Okay, of a system. For example, you have a piece of paper. Let me find a piece of useless paper. Okay, here. Alright. Okay, so I have a piece of useless paper here. Now, this is in order, right? This one is have an order here. This one is order. Is square, the measurement is perfect, is everywhere straight line. So when I do like this now, what happened here? What do you see? You have disorderness, right? The shape, the size are different, the mass also different. They are not in a more order like we know before. But of course, when you put them back, you need to do some work to put them back. So in this case, this is more disorder than before. All right. Another example can be like this. Okay, this one will be a bit crueler. You go outside your house, look for, you put some food there. Okay, normally sugar, you put some sugar there. Okay, sugar, a cube, sugar cube. So what you do is after maybe like hours, then you start to see ants there, and you know that they are very disciplined, right? They walk and then talk to each other. They're also very socialized. I mean. And they walk here, and then they go to some holes that finally end up disappearing into your house. The angry thing is cannot find a way. Okay, now these are very order, right? Like military marching. The problem is after that, you go and disturb them, you blow them. So what happens when you blow them or you spray them with red set and so on? So after that, you end up something that looks like this. Okay, some here, some here. So these are disorder. Some are already dead. Yeah, some are cursing you. Okay, so this one is in order. Okay, in order. This one is out of order, not in order. So that means if in physics, this one is S1, we call entropy 1. This one is entropy 2. So there is a change in entropy. So when things come to not in order, we say that the disorderness is higher. Okay, the disorderness is higher. So disorderness of number 2 is higher than disorderness in number 1. Even though this is order, this one is in order. But if you have seen N line up like military marching like that, all in the same thing, then you better start worry about your future already. Okay, so this one is perfectly in order, right? You see N move like that, only in cartoon you see. Now, this one will be even more in order than this one. Or in other words, we say that this one is more disorder than this one. This one is more disorder than this one. Okay, so that means you see, we are using the relative condition between them. There's nothing called absolute entropy. There's no such thing. We only have change in entropy. That is more important. So the more it go towards this one, the more random things become. Okay, so in the whole universe, what happens is after you use up certain amount of energy, all the energy are wasted and so on, and then things get even more and more disorder. So that is what happens in our future. The whole universe will come to a death of heat. The death of heat, because things is going wasted, do work to do this and that, and finally, of course, it will take like maybe trillion Googleian years, okay, for that to happen. Well, anyway, that is just theory only. Okay, so that is our statement. Okay, so that's it. So you have finished everything in your syllabus. Okay, anything in your syllabus except one thing. Okay, except one thing. Okay, I will WhatsApp you for that. Okay, not here. All right. Okay, so see you again.